Section: Introduction. In this section, we discuss the significant advancements brought about by large language models, LLMs, in artificial intelligence, particularly in their ability to perform various tasks, including mathematical reasoning. We recognize that evaluating and improving these reasoning skills has become a key focus in developing advanced language models. To effectively assess LLMs, we need reliable and verifiable evaluation benchmarks. Reliability means that the problems and solutions must be carefully crafted to ensure accuracy and consistency, avoiding any ambiguities or biases. Verifiability requires that the evaluation process is easy to replicate and validate, allowing us to compare model-generated answers against correct ones efficiently. Many existing benchmarks use a single answer format, which simplifies the evaluation process and enhances reproducibility. For instance, answers are often presented in a standardized way, like stating, "The answer is boxed 3." This method helps us assess the mathematical reasoning capabilities of LLMs across various datasets. The main goal of these benchmarks is to identify the limitations of LLMs and guide future research. We note that several high-quality mathematical benchmarks have been developed, such as GSM-8K, which have significantly advanced LLMs' reasoning abilities. However, many of these benchmarks are becoming saturated due to rapid advancements in LLMs. For example, GSM-8K, once a standard for early models, is now largely mastered by the latest models. Similarly, other benchmarks designed to challenge top models have also reached saturation. This situation is worsened by the emergence of models that promote step-by-step reasoning, which can outperform existing benchmarks. To better evaluate advanced reasoning models, we need more rigorous benchmarks. The AMY dataset has emerged as a more challenging benchmark, incorporating problems from the American Invitational Mathematics Examination, which are difficult for current models. However, AMY has limitations, including a small number of problems, a performance ceiling that is being surpassed by improving models, and a lack of multilingual problems. To address these issues, we introduce OlymMATH, a bilingual mathematical benchmark designed to assess LLMs reasoning at the Olympiad-Level. OlymMATH consists of 200 carefully selected problems in both English and Chinese, divided into easy and hard categories. We ensure that all problems are sourced from printed materials and verified by experts, requiring precise numerical answers for reliable evaluation. OlymMATH covers 4 major mathematical fields, allowing for a comprehensive assessment of reasoning tasks. Through extensive experiments using OlymMATH, we find that even the most advanced models struggle with our benchmark, achieving low accuracy on the hard problems. Our multilingual analysis shows that models perform better on English problems than on Chinese ones, emphasizing the need for multilingual evaluation. We also conduct case studies that reveal some models use heuristic guessing rather than rigorous reasoning, highlighting the importance of evaluating the reasoning process itself. In summary, we present OlymMATH as a rigorously verified dataset for assessing LLMs' mathematical reasoning capabilities. Our benchmark features parallel English and Chinese problem sets for thorough multilingual evaluation. Our findings indicate that current models face significant challenges with complex mathematical problems, and we provide insights into the impact of language on reasoning performance. Section Summary. In this section, we discuss the development of OlymMATH, a bilingual benchmark designed to rigorously assess the mathematical reasoning capabilities of large language models, LLMs, using Olympiad-level problems in both English and Chinese. Our findings indicate that even state-of-the-art models struggle with this challenging dataset, highlighting the need for continued advancements in LLM reasoning abilities and the importance of multilingual evaluation. Section: Benchmark Construction. In this section, we describe the OlymMATH dataset in detail, covering how it was created, the types of problems it includes, the distribution of categories, and our evaluation methods. Our dataset is designed to provide a solid and verifiable benchmark for evaluating the mathematical reasoning skills of large language models, LLMs. We also provide 2 parallel evaluation sets with 200 problems each in English and Chinese to help compare performance between the 2 languages. The OLYM dataset consists of 200 high-quality mathematical problems at the Olympiad level, carefully selected from printed sources to ensure quality and originality. We gathered these problems from reputable sources like specialized magazines, textbooks, and official competition materials, avoiding online forums to reduce the risk of data contamination. This approach guarantees that the problems are challenging and representative of advanced mathematical reasoning, while also limiting prior exposure on public platforms. Thus, OLYM serves as a reliable benchmark for assessing ILM's abilities in solving complex mathematical tasks. To cover a wide range of reasoning skills, the problems in OLYM are divided into 4 main mathematical areas: algebra, geometry, number theory, and combinatorics. We chose these areas because they contain difficult problems that can often be verified with simple answers. While geometry problems usually depend on figures, we reformulated them into text descriptions to fit our evaluation framework, excluding those that couldn't be converted. We aim for diversity within each field. For example, in algebra, we include problems on inequalities, sequences, and trigonometry. We also categorize the problems into 2 difficulty levels: easy and hard. The easy problems challenge standard prompting methods, while the hard problems test advanced reasoning capabilities in state-of-the-art models. The OLYM dataset follows a format that aligns with commonly used datasets, making it easy to integrate with existing evaluation processes. Each problem is organized clearly to facilitate efficient processing. All problems are text-based, and we have carefully crafted descriptions for geometry problems to ensure that all necessary geometric relationships can be understood from the text alone. To maintain a consistent evaluation, we limit answers to real numbers and intervals, simplifying the verification process and reducing ambiguity. We avoid answer formats that are harder to verify, such as complex numbers or free-form text, to keep our evaluation framework clear and standardized. This standardization allows for reliable verification using specific tools. To make the evaluation more challenging, we select problems that lead to complex numerical answers, requiring a summary of all possible outcomes. This approach helps us assess whether models consider all scenarios and effectively demonstrate their reasoning skills. The OLYM benchmark initially features problems in Chinese. To support bilingual evaluation, we keep both the original Chinese and translated English versions of all problems. Our translation process uses a 2-stage approach. We first generate English translations and then refine them through multiple reviews until they are polished. Expert human annotators verify all translations for mathematical accuracy and fluency. The parallel evaluation sets, OLYM-N, English, and OLYM-ZH, Chinese, allow for systematic comparisons of reasoning abilities across languages, while the combined sets are referred to as OLYM, full set. Section Summary. In this section, we detail the OLYM dataset, which consists of 200 high-quality mathematical problems designed to rigorously evaluate the reasoning capabilities of language models, ensuring a diverse representation across algebra, geometry, number theory, and combinatorics. We also provide bilingual evaluation sets in English and Chinese, employing a meticulous translation process to facilitate comparative analysis of model performance across languages. Section: Experiments. In this section, we evaluate the performance of leading reasoning models using the OLYM benchmark and analyze their capabilities in detail. For our experimental setup, we assess a variety of large language models, LLMs, including both open-source and closed-source options. Our open-source selections are DeepSeek R1, DeepSeek R1 Distill Qwen 32b, and QWQ32b, while we include O3 Mini, High, as our closed-source model. To simplify references, we use the abbreviation Qwen 2.5-32b R1d for DeepSeek R1 Distill Qwen 32b. For evaluation, we employ 2 metrics, pass at 1 and cons at 10. Our approach involves generating 10 different responses for each model per problem, except for O3 Mini, High, which we limit to 3 responses due to API stability. We calculate the pass at one score by averaging the accuracy of all responses. For cons at 1-0, we use majority voting to find a consensus answer and then average the accuracy across all problems. We set our generation hyperparameters based on established practices, while for API-evaluated models, we use their default settings to optimize their reasoning abilities. This method effectively assesses model performance, though there is still room for improvement in accuracy and reliability. When we analyze the results on OlymMATH, we find that all models perform poorly, with O3 Mini, High, only achieving 30.3% on the Olim and Hard set. This highlights the benchmark's difficulty, which requires strong reasoning and a deep understanding of math. In contrast, performance on Olim and Easy is better and similar to AMY 2024 and AMY 2025, indicating that Olim and Easy is suitable for evaluating less advanced models. We also notice that language affects reasoning performance, with models generally performing better on English benchmarks, likely due to the dominance of English in pre-training datasets. To compare Olim with other benchmarks, we analyze various LLMs on -500, AMY 2024, AMY 2025, and HMMT 200-2502. Results marked with an asterisk come from reports or third-party sources. We also report the average response length from DeepSeek R1. Our findings show that models score lower on Olim due to its higher difficulty compared to previous benchmarks. While LLMs achieve high scores on -500 and AMY 2024, Olim's varied performance allows for better differentiation of reasoning abilities. For example, DeepSeek R1 and Qwen 2.5-32BR1D have similar scores on -500 but differ significantly on Olim and Hard. We analyze the response lengths of DeepSeek R1 across benchmarks to further assess Olim's difficulty. The model generates more tokens for Olim questions than for AMY 2024 and AMY 2025, indicating that Olim requires more extensive reasoning. Even correct answers involve substantial reasoning, with average character lengths of 39,024 for Olim and Hard and 29,132 for Olim and Easy. The reasoning length distribution for Olim and Easy is similar to AMY, while Olim and Hard has a much greater average response length of 42.8K, emphasizing the benchmark's high difficulty and the greater reasoning demands it places on models. Section Summary. In this section, we evaluate the performance of various large language models on the Olim benchmark, revealing that all models struggle significantly, particularly on the harder problems, which require advanced reasoning skills. Our analysis also indicates that language influences model performance, with English benchmarks yielding better results, and highlights the Olim benchmark's higher difficulty compared to other tests, as evidenced by longer response lengths and varied accuracy across models. Section: Rigorous Reasoning or Empirical Guessing? In this section, we discuss our observations during problem collection and preliminary experiments. We noticed that large language models, LLMs, sometimes make empirical guesses instead of engaging in thorough reasoning. For certain math problems, these models can arrive at correct answers by recognizing patterns, using shortcuts, simplifying propositions, or even fabricating responses, rather than following a systematic approach. For example, in one case, the model, O3 Mini, guessed that two variables were equal due to symmetry while tackling a geometric optimization problem. Although these guesses can lead to correct answers, they lack the rigor of logical reasoning and would likely be seen as incorrect or incomplete by human evaluators. This issue becomes significant when we use rule-based evaluations or LLMs as judges, as neither can effectively measure the quality of rigorous reasoning. We need to be cautious about LLMs taking shortcuts, solutions that are not well-founded, which could create a false sense of accuracy. We further explored this in the AIME 2025 and Omni benchmarks with the O3 Mini, High, and found similar patterns. Despite improvements in performance, LLMs still struggle with deep thinking, highlighting the need for process-level supervision or evaluation, which is difficult to implement due to the high human effort required. Currently, We do not have a precise measure of how many empirical guesses are made in these benchmarks, making this an important area for future research. Interestingly, when faced with problems from our dataset, these guessing strategies often fail. For instance, in one example, the O3 Mini High tried to solve a complex optimization problem and incorrectly assumed symmetry, resulting in an answer of 3081, while the correct answer, verified with Mathematica, is 2625. The OLIM hard test samples are generally more difficult than those in existing benchmarks, as the reasoning steps are harder to bypass through guessing.